Okay. All right. Let's take a look. Let's take a look. All right. So I hope you guys are doing okay. It's Friday, and thank you guys. I appreciate you for being here, and those of you watching online, I appreciate you watching online, even though I'm like forcing you with the view quiz. But anyway, prior to the midterm exam on Monday, we talked about this concept, and we said, hey, we can apply the Metropolis algorithm towards deciphering a message. Okay, so we want to decipher a message, and so let's say this is the text that came in. Okay, let's say this is the text that came in, right? This is the message that we intercepted, and we want to say, hey, what was the original message? What was the original message? And so we said, well, we can apply a substitution cipher, and we could say, hey, what if this was the original message? Okay, all right, what if this was the substitution cipher, the code, the key code? Then if this is the correct mapping, it's not. But if this were, then the original text would have been this, right? KBDKE, because K goes to, because our original text is ZTRZY. And so K becomes Z, and B becomes T, and D becomes R. And so if this is the message we intercepted, then this had to have been the original message, okay? And we say, okay, well, do you think this was the original message? KBDKE, OQFAKD, OQFDGCK. Do you think this was the original message? Probably not. I mean, not a zero probability, but a very, very small probability that the person really wanted to send this strange thing, right? We're working under the assumption that the person sending the message speaks English and is probably writing a message in English, okay? So we're going to evaluate the probability that this text was the original message, and we used Bayes' rule, and we said, hey, what is the probability of this message? Okay, and we're going to say it's going to be proportional to the probability that this was the message, okay, multiplied by the likelihood of the we have the likelihood of the data, okay, which is basically this, given the mapping, and then we're going to multiply it by a constant and divide it by a constant, because we're saying the prior probabilities of any particular letter mapping, no one particular mapping is more likely than another, so we're going to just keep that to be a constant. And then the marginal probability at the end is also a constant. And so we're going to just say the probability of some cipher key mapping given the text is just going to be proportional to the text given the cipher key mapping. Okay, so this is kind of, I think, where we left off on Monday. Right? On Monday, we said, hey, and the reason why this is so great, why is it so great? Just to get something proportional? Because in Metropolis algorithm, we don't need the actual function, right? In the Metropolis algorithm, when we figure out P move, that is probability of the proposed location divided by probability of the current location, we only need something that's proportional. We don't need the actual exact form, which would require us to figure out all of these constants, these normalizing constants and things like that, which we said, hey, that's a lot of work to try to do, okay? So the fact that we don't have to figure out those constants, that's great, and we're going to use the Metropolis algorithm. And so we said, okay, well, how are we going to evaluate the likelihood of the text? We said the likelihood of the text is a combination of kind of two things going on, okay? One is we're going to look at the two-letter combinations. We're going to say, how likely are we to see the letter KB, right? And the letters BD, right? So we're looking at, right, we got KB, BD, DK, KE. We're asking, what's the probability of seeing these things, okay? And so we say, okay, well, how often do you see the letter K followed by B? And we say, well, sometimes, right? Like in the word blackboard, okay? The word black ends with a K and board starts with a B, and I think it's one word, so you'd see a KB combination, right? And how often do you see these? And we can probably think of some words that can contain these combinations, but we said, very common letter combinations are TH, things like that, EN, IN, ON, those are all very common, stuff like that, okay? And so what we had done was we said, we had the computer read through War and Peace, the English translation of War and Peace, count up every single letter combination, and we got that, right? Now if we took a different book, right, if we had it read through maybe 10,000 random pages of Wikipedia, we could also have it do that, and maybe we'd get some different things. We could have it go through scripts of movies and TV shows and stuff. So it doesn't really matter, but just, it might make some effect and some differences here. Okay. And then when we go through our text, what we're going to do is we're going to look up in our table how likely KB is, and it says it assigns a probability KB. How likely is BD? It assigns a probability BD. How likely is DK? It assigns a probability to DK. And we go through every single thing here, and if it was a probability, we would just multiply all of them together. But if you multiply a whole bunch of tiny probabilities together, we run into problems on the computer, right? So the computer has floating point limitations, and this is a situation where you run into floating point limitations, right? I forget, what's the smallest value that the computer can represent? It's double X min. It's like 10 to the negative 52. I don't know. That's how many manticipits we have. Well, anyway, it's really small, okay? 10 to the negative 52 times 10 to the negative 1020, no, 10, I don't remember. Okay, we covered it on 102A, right? And I made you do homework on that and stuff. But anyway, so you're going to run, if you keep multiplying all of these tiny probabilities together, you run into the issue here. So what we do is we turn it into logs, right? A log of a tiny probability is just a negative number. And then you can just add a whole bunch of negative numbers together, and it's no problem, okay? Add a bunch of negative numbers. All right, and then the other way we are going to evaluate the likelihood of our text is we're going to say, hey, if we see some real words show up, right? Like if I look in here, I say, are there any real words? I guess GE, maybe. Doc, DOK, that's not a real word. Okay, we don't really have any real words here. WB. Maybe we're talking about TV or something. But if we did see some real words, right? Like if one of these things turned into the, THE, we would go, oh man, that suddenly makes us quite a bit more likely, okay? So we're gonna look through there, and we're gonna use a lexical database, and I think I compiled this from Wiktionary. Let me, so right now, this is where we are. We have this matrix of two-letter probabilities. Oh dear. Let me magnify my text here. Okay, so if we say, what was the intercepted text? The intercepted text we have is this. Okay, and then with our current mapping, the current mapping says the text that we intercepted is ZTRZY, and right now with our current mapping, we would say the original text was KBDKE, and we say, well, that doesn't make sense. Okay, but we want to say, okay, well, what's the probability of this? Okay, and we went through and we have this two matrix, this matrix of two-letter combinations, which we're trying to get here, and we're saying, okay, HE is common and TH is common. And so how do we do this? Okay, we go through the text, we're going to give it KBDKE, okay? And so we can see, if I write this, okay, so we can say, all right, this is called two-letter log probability. Two-letter log probability, and I give it the text, let's say THE, okay? And it says the probability of getting THE is, the log probability is -14, okay? Versus if I say XYZ as just some combination of letters, that is less likely, -44, okay? And I don't know, is there some other combination that's even less likely? JXJ, okay, that's even less likely than XYZ, okay? And I wonder what is THE the most common? THT? No. HEH? No. Okay, well anyway, maybe just TH. TH space. Okay, TH space is even more likely. Okay, but anyway, so we're trying to do this, and obviously, if you put in a long thing, okay, like you can have the quick brown fox, okay. The more letters, it becomes more negative, right? But if I just do a bunch of gibberish, okay, that's more negative, right? And so we say between these two things, this one is more likely than this one. Now you look at the numbers, -120 versus -143. It doesn't feel like a huge difference, but remember, these are logs, okay? So when you exponentiate these, it's a very big difference, right? One is e to the 23 times more likely than the other, okay? So as far as probabilities go, it's a very, very big difference. All right, so anyway, this is the function, two-letter log probability. You put in text and it reads through the text and it basically matches up in this table the things and it returns back a log probability. Okay, and then we're also going to load in this lexical.rdata database thing. And I think, let me look up. Lexical database, $word. Oh, okay, so how does this work? So we're going to look up some words here. So I think I can look up, say, the word A. No, that's not how it works. Hold on. I forgot how it works. Okay. Oh, okay. So we have basically the word and the probability. So I'm going to go through the word A, and so here if I do log probability of words, Okay, I think I say, if I do the house, and I have to provide it lexical database, okay, it tells me, okay, that is -10. All right, so these are right. The will be very high probabilities, right? So if you put in like super common words, right, like to the, okay, it's very, right, very high probabilities, okay. But then if you put in something like gibberish, okay, I think it gives you -23. And if you put in like multiple gibberish words, okay, each gibberish word that it doesn't find, I think it puts in -23. So not 0, but we keep doing that, right? And if one of these, and you can say, okay, what's the probability that you get the house versus the mouse? What is more common, house or mouse? Okay, house is more common than mouse. Okay, I feel like I'm Dr. Seuss here. Okay, the house, the mouse, the louse. Okay, the louse is even less common than mouse. And we can even ask, what about grouse? Okay, oh, grouse is more common than louse, but less common than mouse. Okay, and so anyway, we can start putting in words, okay, and see how likely some of these things are. All right, so this thing is going through the lexical database, which again is kind of a listing. I guess I got 92,000 words in here, and we have the word A and AA and AAA. Let me just see. It's a data frame. Okay, these are the kind of the probabilities. And how do I find, so let's see if we can find where lexical database word is equal to house. Okay, so the probability of house is that houses is a little bit lower, housing, household. Okay, so each of these kind of words, they each have different probabilities associated with them. Okay, and we can take these things and throw them into. So we can say the house, the houses, and each of these things change the probability. The housing, the household. Okay. The pant versus the pants. Okay, pants are more common than pant. Okay, so anyway, so we want to try to figure this out. We're going to throw our words in here. Okay, is this all right? So basically, I got two functions that you put some text in, and it's going to give you back a number based on either the two-letter combinations, okay, or the words that appear. Okay, and we're going to multiply one of these things by a scale, so we can kind of fine-tune whether we want to put more importance on the two-letter combinations or more importance on the appearance of real words. Okay. All right. So the scale is a factor to balance whether we favor more common letter combinations more or less than real words, and the scale factor for the words will be small because the log likelihood of the words is very negative, while the log likelihood of even the very uncommon letter combinations is not too small, considering that there are only 729 possible words, right? So if you think about, or 729 possible letter combinations, even the most uncommon letter combinations won't be that small. So we kind of have to scale all of these things down, okay? So again, if we were to just try to do a brute force method and just try all of these things, this would be very, very, very inefficient, okay? But, and so the probability of just by random chance, hitting a good mapping is going to be very, 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 very low, right? Because if there's a total of 26 factorial, something on the order of 10 to the 26 possible mappings, and if you just randomly try one out, and you say, well, that was no good, let's randomly try another one out, that was no good, let's randomly try another one out, that was no good. You're not going to hit anything good. So what we're going to do is we're going to use the Metropolis algorithm, right? So here are just 3 totally arbitrary mappings, and if we were to do this and we were to apply this, these are all junk. How are we supposed to find a good mapping, right? So I said, here's one random mapping, this is what we got. Here's another random mapping, this is the original text. Here's another random mapping, here's the original text. None of these are good. So what are we going to do? We're going to use the Metropolis algorithm, okay? And what we do is we say, all right, let's just start off, right? Metropolis algorithm, we said we can start off in a terrible location, but eventually it might find a good location. So what we're going to do is we're going to just start off with our current terrible mapping, and we're going to propose a new location, right? We say this is bad, but let's try taking a small step and see if that is any better, okay? Now, what does a step look like when we're talking about letter mappings, okay? What we're going to do is we're going to just say, okay, currently, A maps to H and B maps to T and so on and so forth. But what if I just swapped 2 letters? What if right now G maps, or B maps to G and E maps to O? What if I swapped these things, so E maps to G and B maps to O? What if I did that? Okay? And so the original text was ZTRZY, and the original, and the coded message we got was ZTRZY. Okay, but swapping this, saying that, what was it? The letter B maps to O, okay, or O gets mapped to B, means the original text here, when we got RB, had to be DO, okay? R, right now, R goes to D, and B goes to O, okay? And over here, R goes to D, but B goes to G, okay? And so this swap, switching where B maps and O maps, or I'm sorry, G and O map, if we swap those, suddenly, the text, it's still complete gibberish and trash, but this one looks a tiny bit better than this one. Or a little, I mean, it looks, when we evaluate it, when we throw it in there, we get a less negative number, okay? So this ZTRZY, still the original text would be KBDKE, KBDKE. That's not affected, okay? But places like here, the RB goes from DG to DO, okay? And then TBR goes from BGD to BOD, right? And so now we have things that like, oh, this isn't better, but this looks a little bit more like it could be English, right? I see the words do, and I see bod, and do again, and things basically, we've got O's popping up where it makes sense for there to be a vowel, right? So just comparing these two, we'd say, okay, this mapping down here is better than the mapping up here. Do we agree? Okay, and that's it. That's how the Metropolis algorithm here is going to work. We're just taking our current location. We're going to say, let's propose a small change. We're not trying to go for the gold. We just want to do a little bit of improvement, right? And this is a good strategy for life, right? You feel like, oh, things aren't going great. You don't have to suddenly say, I'm going to change everything about my life and make it better. You just say, hey, can I make a small change? And if it's better, let's stick with it, okay? And so that's what we're going to do. We're going to just bring in a small change here. We're going to swap the G and the O from the B and the E to the B. Okay, we're going to swap these two letters, and we're going to say, hey, this, my thing is broken. Okay. No. What happened? Hang on. Okay, my touch screen works, but my keyboard does not. Grrr. Okay. Hang on. Well, let me keep talking, and then I'll try to figure out this keyboard issue. All right, so we're going to say this proposed mapping is better. Okay, oh, I completely forgot. I need to give you view quiz answers. All right, the first two are D as in dog, and the second one is B as in bear. D as in dog, B as in bear. Okay, D as in dog, B as in bear. Okay, is that all right? All right, and then so if you take your log probability, turn it back into a probability or whatever, you get a probability greater than 1. The probability of the proposed location is higher than the probability of the current location, so we're going to accept this proposed mapping. Okay, we're going to accept this proposed mapping. We can also still accept proposed mappings that are worse, right? So if we swap letters and the proposed mapping ends up a little bit worse, we can still accept it, okay? And that's going to happen with probability P proposed divided by P current. Okay. All right, and because we're dealing with small probabilities, we can run into machine epsilon problems with the computer. So rather than using the actual proposed, right, we have a negative probability, and rather than raising e to the negative 1,000, we're going to just leave it as logs. And the equivalent is we take the difference in logs and we ask if the log of some random uniform value is less than the difference between logs. So how do I highlight this? Okay, so rather than doing P proposed divided by P current, I have log of P proposed minus log of P current. Okay, and then rather than comparing U, we'll compare log U. Okay, and so this is what we're going to do, all right? So this Metropolis algorithm is great because we're building off of previous states rather than true random sampling. If we had to do true random sampling, we have a 1 in 26 factorial chance at hitting the correct mapping by chance, so that's almost never going to happen, okay? And so instead, we're going to take our current mapping, we propose a letter swap. If it's better, the Metropolis algorithm will take it. If it results in a lower probability, sometimes the Metropolis algorithm accepts it. Okay? And so just naturally, it's going to gravitate towards areas of higher probability. Okay? And so, like in the homework, you had a Metropolis algorithm where we started off at 100 and it kind of just gravitated towards a better region, you know, where the normal values are. So it's kind of like this. We're just starting off at some arbitrary location. We say, we know it's bad, but can we just get a little bit of improvement? Okay? Now, technically, this is an optimization problem. We're trying to maximize the probability of the original text, okay? And the Metropolis algorithm is used to kind of produce random samples, right? So you think, well, why are you using the Metropolis algorithm, which is used to produce random samples, to kind of do this optimization problem? Well, it's still effective because we want our Metropolis algorithm to produce random samples of areas of high probability, right? And so if we think about areas of high probability, pretty much all of these other letter mappings are absolutely terrible, okay? And so we just started off, it's giving us terrible things, and then it's going to get to the region of high probability, which is basically going to be the answer that we want. Okay. I'm not sure how to deal with the fact that my keyboard has broken. All right, I think I have to restart my computer or something. I'm getting a, oh dear.